Broadcasting from the campus of Lynn Benton Community College. We are the Mid-Valley STEM-CTE Hub. I'm your host, Casey, and this is Closing the Gap. Welcome back, everyone. This is season 4 of Closing the Gap. This is our first episode of the season, and I'm really excited to have you all back. Thanks for jumping back on to listen. At the end of last season, I had mentioned we had this brand new studio that we were all excited about to record in, and everything was going to be in person. Well, it is. But this first episode is back online, but the audio quality is going to be worth it. I think you're really going to like this one. I really enjoyed talking to this person. They were very interesting. I think we're going to touch on some really cool subjects that we have not heard from before. So I would like to introduce our guest today, Margaret Landis. Margaret is a research scientist at the Laboratory for Atmospheric and Space Physics out of University Colorado Boulder. So without further ado, let's get to the show.
Thanks so much for the introduction, Casey, and happy to be here.
I would love to hear a little bit about the types of topics you research.
Sure. So I started out kind of an undergrad doing Mars science, but since then I've done projects on Mars, Ceres, which is the largest asteroid in the asteroid belt, and the Moon. And my general research focus is looking at signs from remote sensing data of where water and other types of ice have been in the inner solar system. And the reason we care is a longstanding question in planetary science is where the Earth got its water from. We are personally made of about 70% of that stuff, so it's a really important thing to understand where that came from, to understand both how life on Earth works as well as how other planetary systems work. So even if I'm not active in exoplanet research, the things I kind of care about are the things where we can kind of ground truth potential observations as close as we can to really ground truthing observations for exoplanets.
Awesome. What do you do with that kind of information?
So generally, one big question we have in planetary science is where water ice initially formed in the solar system. So there used to be a concept in the past based on thermophysical arguments, so basically looking at temperatures, where water ice appeared to start being stable based on what we understand about the sun, kind of somewhere in the asteroid belt. And initially, observations of Ceres and Vesta, which were both targets of the Dawn mission before robotic exploration, showed that Vesta didn't have a whole lot of water, but Ceres did. And so there was some evidence to suggest that maybe the so-called snow line in our solar system fell between Vesta and Ceres. A lot of that has been upturned in probably significantly the last 20 years. We've started to observe more exoplanetary systems where exoplanet solar system structures are not like ours, where there's more that we observe with big giant planets closer into the star. And we also, probably about 20 years ago now, there was a dynamical model that was developed in Nice, France. So when you see it written, it looks like the NICE model, but it's really the Nice model. Which feels a little self-congratulatory if you call it the NICE model. But anyway, it's a dynamical model that suggests that the outer planets kind of in our solar system readjusted themselves at some point early on in solar system history and scattered a lot of smaller material into the inner solar system. So if this happened, then maybe some of these icy objects in the asteroid belt are actually introduced from the outer solar system. There are some low temperature mineral formations on Ceres that suggest that Ceres might have actually formed somewhere around Saturn's current orbit. And that then begs the question, did any of that material make it to the Earth? And is any of the water on Earth kind of remnants of that? So the idea is that we're kind of picking at this larger solar system structure problem by looking at where water ice is present today on the Moon, Mars, and at least for me, Ceres, but generally in the asteroid belt.
Awesome. Is the goal to just gain as much information as possible about the planets in our solar system?
Definitely. And addressing this question of where water particularly is. This has been a major focus of NASA, especially in Mars exploration science for the last 30 years or so. But as far as we're aware, water is really important for life as we know it, as well as being a material that, if you go to the orbit of Mercury, water is not stable at current temperatures on Mercury. So trying to understand potentially how water was reintroduced to the inner solar system, if you even require that, or if melting rocks or having volcanic outgassing is sufficient. And so we're really getting into these key kind of, it's sometimes it feels like a stretch to call them geological processes, because we're thinking instead of locally, like the entire planet outgassing from volcanism, but we're trying to understand if planets intrinsically can kind of produce water from them, or rocky planets themselves can produce water themselves from melting their interiors, or it has to be delivered in. And these are kind of, I don't know, I say a lot that if there was a Nobel Prize in planetary science, if you could answer that question, is most water from an object itself or redelivered, that would be the Nobel Prize for planetary science. There isn't one in planetary, so you kind of have to find your external congratulations elsewhere. But these are one of these kind of fundamental questions of planetary science that we're trying to answer. The challenge is doing it all at once is really hard, and what I really like about planetary science is we have so much remote sensing and robotic spacecraft data at this point that we can really start to answer pieces of these questions that start narrowing down the possibilities, or helping us understand what possibilities are plausible versus less plausible.
Awesome. You were talking about using robot data. Are you working with any specific robots that are out in the solar system right now?
Yeah, a couple. So in graduate school, I started working on data from the High Resolution Imaging Science Experiment on Mars Reconnaissance Orbiter, so MRO's HiRISE. That is a Mars high resolution camera run out of the University of Arizona. And in graduate school, I started not only working with the data, but also planning new observations, which was for a kid who watched the Mars exploration rovers land in middle school and went, oh, I want to do that, was really nice. And like that was a good experience. And that's also when I started knowing that this is kind of what I wanted to do with the rest of my career. I'm also on the science team of the Lunar Reconnaissance Orbiter Diviner Lunar Radiometer. It's basically a forehead thermometer for the moon. And I also was on the Dawn at Ceres mission when it was operational from 2015 to 2018 when we ran out of fuel. So been on a couple. Dawn is still in a 50-year stable orbit around Ceres, so even if we can't talk to it, we know it's there. And so even if that mission has ended, it's still kind of, it was a major spacecraft in my career, and so it still probably exists in orbit around Ceres, so I like to count that one too.
Oh, that's incredible. I feel like you just gave so many really interesting nuggets that I would like to branch off on, but just to keep us on track,
Yeah.
I kind of want to get into your current role as a research scientist with LASP. And do they give you topics to work on for your research papers, or do you come up with your own topics? I noticed on your profile that you had quite a few credits to your name.
Yeah, I try to keep myself out of trouble by publishing research papers at a decent cadence. It's a little bit combination of both. So in planetary science, generally, a lot of the work that we do, unless we are a faculty member or at a NASA center, tends to be very self-directed and funded by, especially funding from NASA. And for those, we propose our own research questions using data or simulations to understand fundamental planetary science questions. And in that way, it's very self-directed. So if you kind of see a topic that is an area that no one has explored before, it's definitely fair game to write a proposal and fund yourself doing that. The flip side is in some of these larger collaborations, especially with large spacecraft collaborations, there are fundamental questions that mission wanted to answer. So since Dawn's wrapped up, I think that's a good one to use examples from. One fundamental question for Dawn at Ceres was understanding how much water ice was in the near surface and how that affected the evolution of that asteroid over a long period, or dwarf planet. Ceres has been so many things in its history. It's kind of like Pluto, except it happened first. It's demotion and then repromotion to asteroid. But one of the fundamental questions at Ceres was understanding the water budget in the near surface and understanding what that meant for previous telescopic observations of Ceres. So in the 80s, 90s, and mid-2010s, there were ground-based telescopic observations of a of water vapor around Ceres. And it was very tenuous. These were kind of almost one-off observations, except they were repeated over a 30-year time period. And it suggested that Ceres might be outgassing like a comet, but in a very reduced way. So this would be losing its water to space over time. Um, and a lot of the thermophysical models, so models that look at the surface temperature of Ceres and the interior temperature of Ceres, predicted this would happen, but it's not happening consistently. So one mystery was, is Ceres really as icy as we think it is, which we kind of confirmed. And then another one was, does anything match the kind of exosphere telescopic observation? So an exosphere is an atmosphere that doesn't collide with itself as often as it escapes to space. And so that was kind of a niche that my advisor at the time and I identified. He did most of the writing because I was a graduate student, didn't know how to write proposals, but I read it and had some comments, a proposal to look at that role. And so what can happen on NASA missions is you set up your initial spacecraft team in advance of launch. So this can be 10, 20 years before you arrive at your target, because it also takes several proposal rounds to win. Right. So like some of these people have been working together forever, but I think we as at least US-based community and NASA have realized that if you are forming your team 20 years in advance of when you actually get there, that's 4 or 5 generations of graduate students. And so there might be expertise that you realize later that you need, or expertise from people who were not in the field at the time because they were in high school. And so there are programs to then join these big collaborations. You have to identify a problem that the collaboration has identified as interesting that might be a niche that you can fill. So that's what we did to join the Dawn team. And I ended up doing my first postdoctoral appointment with the gamma ray and neutron spectrometer on Dawn, or gamma ray and neutron detector grand instrument on Dawn. So some of it self-directed, other times to fit into one of these big collaborations, you basically go, here's a niche I can fill. Dear NASA, may I have some money to work on this? And then you join the collaboration, and then your collaboration, like I was mentioning, I did a postdoc with a different instrument on the Dawn team, grows into something else. So it's a mixture of both, and it depends on what kind of collaborations you're in. But no matter what, I think one thing, especially with planetary science, is that we use data from a lot of times from spacecraft that we did or did not build. So it's very much a community effort one way or another. So yeah, the resources we have are very much things that came out of larger efforts and collaborations. So as much as, there's this idea of the scientists kind of just going off and doing their own thing, especially in planetary, that's not exactly what we do, because even if we think we're in our office just having pure theoretical thoughts, the data to test that come from these large community efforts. So it's a combination, and I know I like to keep a little bit of different things going on just to, I was about to say keep it interesting. It's always interesting, but have some variety. So I'm not in my office all day, not talking to anyone, but also, having some moments to just sit in my office and think more theoretical thoughts.
For sure. It sounds like there's a lot of independent work that goes on, but you mentioned collaboration, and is there any sort of formal meetings, sit downs that people in your position will do with the whole team that's working on Dawn, for example? Do you ever have to get together and actually sit down and have a meeting?
For sure. So this used to happen a lot more pre-pandemic. Obviously, we had to shift modalities a little bit to make sure everyone was safe, especially because a lot of these spacecraft develop specialized software, and maybe 4 people in the world know how to use it and implement it. So we want to keep them safe. Yeah, so a lot of these spacecraft science team have periodic team meetings, and these are always really interesting because we usually have gone off and for, between 4, 6, or 12 months have been working on something where we've worked with our close collaborators within that team. But at science team meetings, we get to present to the entire science team. And that's always, I find, a lot of fun because you get to find out what everyone's been doing before they write the paper. And so you kind of feel like you're more up on the field than you would be otherwise. And then it's also interesting because both as a presenter and a commenter, you don't always think of everything when you're working with yourself or your 3 closest collaborators. And so it's a really fun interchange to go, okay, so this is really interesting, but have you thought about this? And then kind of building on ideas that way. And then science teams will have meetings, but then there are also a couple of very large planetary science, more general meetings throughout the year that are also really fun because then it's all the different both spacecraft science teams and people who are working independently with different types of data and simulations all come together and present. We just had a asteroid, comets, and meteors meeting in June in Flagstaff, and I had some colleagues who had never been to a conference before, and one of their comments was, "Do you just know everyone here? Are these all your friends?" And I'm like, "Well, it's a 500 person meeting, so it is kind of like 500 of my closest collaborators and friends in the same building, and some of them we hadn't seen each other in years, so of course I'm going to go disappear and like talk to somebody else about a different thing." But these opportunities are really nice ways to then kind of come together for our extroverted introvert time, where we all get to talk to each other, come up with new ideas, and then one thing I really like to do is come up with proposal or new project ideas at these conferences, and then kind of go away, develop them a little bit more, and then next conference or some conference, some number of years in the future, you get to present on those results. So it's really great to do the networking in kind of concert with doing some more independent work.
For sure. It sounds like there are several different modalities of communication that you work within, writing and interpersonal communications. How did you feel about getting training like in writing and interpersonal communications when you were in school? Did you take a lot of classes? Was it something that came natural to you and the types of things that you were already studying?
And that's a really tough one. And usually, advice I give to people who are interested in going into STEM fields is to not skimp on the writing classes as much as you're ready to get into more advanced math or more advanced physics. Science is really cool, but if you can't communicate it to anyone else, it's only cool to you. And that means you don't get to, first of all, share how exciting your discovery is, but then you also can't articulate it and have someone build on it or refine that idea. So, writing definitely is really important. It's one of the things where scientific paper writing is like a genre unto itself of writing. And so getting used to what the tropes are in the genre and how you're supposed to write and how you're supposed to balance. For a long time, there's this tendency in scientific writing to use third person, like the team did this. But you're like, well, the team is me and I'm writing about what we did. So there's, at least in the last couple of years, more of a move towards like active voice of like this, we did this, which of course makes it more interesting to read. But on the flip side, acknowledges that there's researchers participating in the system. And sometimes for scientists, that is a little bit of a shock when they realize that people do science, because I think we have this very popular conception that science has somehow divorced itself from people. And that's not the case. So it's always interesting to run into much older papers that are very brain in a jar, a miracle occurred and this result occurred, and then more recent papers that are like, we went into the field in Antarctica, this is what we saw and found. So it's, like I mentioned before, it's a genre unto itself, and it takes a second to learn it. A lot of the preparation you get in graduate school by actually doing it, and so, you know, the first 2 years of especially a PhD program are like, oh my gosh, do I actually know how to write? And the answer is yes, but you're learning a new genre. So it's like if you asked a science fiction author to all of a sudden, or a hard science fiction author to all of a sudden write historical fiction, it would take him a second to figure it out. And I think in at least college and graduate education in the last maybe 10, 15 years, there's been more of this realization of training people to write well helps everyone, because then when you want to read a paper, it's actually enjoyable and tractable to read, and you can get challenged by the scientific ideas instead of the kind of arcane like hand waving of like there's no people actively doing research here. A miracle occurred and we got this data. So it's definitely in transition, and I think the education is getting a lot better.
That's awesome. Yeah, I kind of noticed like a little bit more of a journalism kind of influence, or like journal writing kind of influence. Yeah, just the personal touch is definitely evident.
Yeah, I've made the joking but not always joking comment that the method section is my diary from having actually done the data analysis. Like today I did this, and then I did this, and then I had lunch. But then you cut out the lunch from the method section because no one cares if you had lunch.
For sure, for sure. So, what type of education is necessary, or like level of education is necessary to become a research scientist? Is it something that you could do with like an undergraduate degree, or is graduate school necessary?
Is graduate school necessary? The great question of science. It depends upon what aspect of research science is the most interesting. So planetary science is fundamentally interdisciplinary, which means that some people have a physics and astronomy background, some people have a geology or a geochemistry background, and it really varies significantly. Like you mentioned in the introduction, LASP itself has existed since the 1940s, which in the grand history of people doing science is not that long. And so in a lot of ways, planetary science is a very young field, and it used to be maybe 30 years ago, it was possible to lead a research group without a PhD. One example is Bob Strom, or Robert Strom. He was at University of Arizona for years and wrote a lot of fundamental Mercury prediction papers that the Messenger mission ended up confirming, and he didn't have a PhD in planetary science because that didn't exist. By the time I rolled around, PhD programs in planetary science did exist. There's still not tons of them, but there are some. And it depends upon what you ultimately want to do with your research career. So there are definitely folks who have bachelor's or master's degrees who are working in planetary science who write papers, but maybe not as many papers, or do a really key function on a spacecraft mission. They're absolutely valuable and critically important to being able to do the kind of work that we do, but they're not running their own independent research lab. To have that kind of self-direction and a little bit more autonomy, a PhD anymore is almost necessary. And it's not necessarily because you've got the right pieces of paper on the wall that you need a PhD to do science for, but it's being able to get one-on-one mentoring for someone who has done a similar job and kind of have it be a job training program. So like I mentioned, a lot of the writing, science writing I learned how to do was in graduate school. And that's because my advisor was reading my drafts going, okay, this is what we need to move here. The organization could use some strengthening or changing here. And so a PhD program in science, and I think maybe some other STEM fields, I can't comment on them because I have one PhD and I'm not going back. You can't make me. It was enjoyable, but it was a really intense 5 years. But generally in STEM fields, it's more of an apprenticeship model where you take classes your first couple of years, but then you start doing your own independent research. And the PhD is more of a sign of, can you do independently directed scientific work and make a unique contribution to the field? So the answer is a PhD is not always critical, but if you want to have your own lab group or self-direct most of your research, that's the path to go down. And I knew that's what I wanted to do in college, which is also unusual. And so I knew the PhD was the route I wanted to go down. That being said, I know plenty of people in planetary who did their bachelor's or master's degrees and went, great, I'm going to work in XYZ technical thing for a while, and then came back to a doctorate going, you know, I want to get another skill to be able to be a little bit more independent in my research, or I want to start exploring a different type of planetary science research. And the way to do that is to go have some time to just kind of dedicate to learning a new subfield. So it really depends. And I think one critical thing to point out in a lot of STEM fields is that graduate education tends to be paid for by someone who is not you. It can be funded through individual departments by you teaching classes while you're in graduate school. There are multiple National Science Foundation or NASA fellowships to apply for, and graduate students get written into grants all the time by the overall advisor or principal investigator of the lab. So generally, if you want to become a scientist, you don't have to take out, or an engineer, you don't have to take out loans for that graduate education. And a lot of time engineers will have their companies pay partially or almost entirely for their master's programs. So that's one difference with kind of phase 2 of science education after undergrad, is that usually you work your way through it either with research or with teaching or with getting a job in industry and having them have a salary, or not a salary, but a tuition benefit program. So I think that's one really key thing. Is it sounds like from my CV I was in school for many years, which is correct. But my responsibility to pay anyone back or pay for tuition ended after those first 4. And that is still generally a pretty typical experience.
I really appreciate that you spelled that all out, because I feel like a lot of reasons that people don't go to school is because of accessibility reasons. And to know that, like, if you could just make it through your first 4 years and, you know, you really want to be a scientist or you really want to be an engineer, that your graduate school would be a lot easier to obtain financially. I think that's great information to put out there for sure. I also feel like I was able to like draw this conclusion between being a scientist and being like a creative professional, where some of the work that you're able to show is maybe more important than the piece of paper that you have. The portfolio that you're able to build with the skills that you have.
Definitely. And I think a lot of ways science as it is portrayed in popular media is like, oh, this genius is in a room with a chalkboard.
Right.
But I think it neglects the fact that a lot of science, especially when you're trying to come up with new ideas or analyze or interpret your data, is a really fundamentally creative thing. Like there's some days where I have thought really hard all morning, and in the afternoon I'm like, yep, I'm done thinking for today. The creative spark has been used up on hype, like super focusing on one thing, and so pacing yourself for having different things to do. Another thing that I think is really interesting in that kind of creative freelancer parallel is that the position I'm in and a lot of quote unquote soft money researchers are in, we're completely supported by grants and from external funding, which means that if you approach us with a project and they ask us to do it for exposure, I think scientists fall into this pit of, or this common pitfall of, well, it's fun, so I'll do it, and I like to do it. My sister has a BFA, and she has been the one to primarily teach me that getting paid in exposure, people die from exposure. So
Right.
think about that the next time you're working on spec. And I think that's one big challenge from a science perspective is a lot of the career pipeline is built towards people working at national labs or federal facilities or faculty positions. And that's generally, there are never enough faculty positions for the number of PhDs who graduate every year. And some PhDs go into industry and have great careers. Some of them stay in academia and have great careers. Some of them go on this primarily research track for a long time before maybe switching between the two. And I think having these survival skills that creative freelancers have is something that we miss in science education. And I always find it humorous when people are like, oh yeah, science and art are totally different. I'm like, what? You're doing something creative that you're deeply passionate about. There's never enough money to cover everything, and you're trying to fundamentally challenge thoughts we have about society and our place in the world. Oh yeah, they're totally different. Of course, there are no commonalities, and that was sarcasm for the listeners online who might not have seen my facial expression there. Yeah, so I think there's a lot of really deep commonalities. And one example is geology. You have to do field sketches all the time, and I went and took an art class because I was tired of my field book looking bad. So there's a lot of overlap, especially with field science.
That sounds like a lot of fun. As someone that is a creative professional, like going around and sketching outside sounds amazing.
There's definitely a personality type that's attracted to geology, which I realized in graduate school, which is like you like to be outside, which is part of my transition from more physics and astronomy into geology is I wanted to think about landscapes I could actually see one day. So that's one of the reasons why exoplanets and galaxies were less interesting to me than being able to see pictures of Mars, because I might do it, the next two generations might not be able to do it, but eventually someone's going to be able to stand on a landscape on Mars and go, how do I think about this? How do I interpret it? How is it similar or different than the Earth? And that's, at least from a geology perspective, the first thing you do is you do a field sketch. So that's, yeah, something to think about and what really attracted me to planetary geology versus other aspects of planetary science.
For sure. Yeah, you had mentioned in email before we met that you were originally thinking about pursuing astrophysics.
Yep.
So what do you like about your job now, or your current position?
I like that a lot of my time I get to think about research projects I find really interesting. Interestingly enough, one of the things I mentioned in kind of the emails ahead of time was I did a research experience for undergraduates in Cambridge on astrophysics. Turns out the wavelengths I was using were infrared wavelengths, which are not too dissimilar from looking at radiometer data now. So I think it's one thing to point out in science is that even if you decide ultimately one subfield is not for you, there's very little quote unquote wasted time in science, because even if you're not looking at young stars and presolar nebulas like I was doing in undergrad for an internship, being able to think about how do you collect data in the infrared, how do you interpret that data, what's the processing pipeline like, is not too different from infrared data of something else. And it's this concept that's been published on a little bit in especially the planetary science kind of professional workforce literature, where it's this concept of a braided stream, where even if you jump out of planetary science for a second, you still are doing valuable things, and you may or may not come back into like the main braid of the stream. But these are ways of thinking about a career that are not just a pipeline where it's not all linear. And so the other thing I really like about my job too is I get to work with data from actual planetary surfaces. One thing I always liked is being able to go, okay, so you have this excellent idea of how you think this thing works. What are ways of testing that? And it's so much fun to be able to test that with actual observations, and with active spacecraft, you get not always a lot of input, but for the HiRISE camera, for example, every 2 weeks I put in the image requests I want taken of Mars for my research. And that is just, that's wild. I've not jokingly told people like that was my dream job when I was a kid, and I can't believe I'm doing my dream job. And of course, you know, jobs are jobs. They're not your entire life, and they don't have to be your entire personality. But being able to do something where I feel like I'm exploring the solar system, but in ways where I'm not actively risking my life is really, I think, what I've always wanted to do. And being able to ask these questions is just really energizing. And so, yeah, that's why I like my day-to-day job, is I get to think about big things, but then also think about really small things, like what lighting conditions do I need on this image on another planet with a giant camera that's orbiting a planet that it's not mine. Like, those are just, it's the excitement, and you never kind of know exactly what data you're going to get back from day to day. You can make reasonable assumptions, but every new image like coming down from the HiRISE camera is like, oh, that's cool. Like 4 people have seen this, and now I get to look at it, and it's a huge privilege too.
Yeah, that sounds like an amazing thing to get these photos that you can like cherry pick what you're seeing. Very cool. I feel like STEM fields are like notoriously male dominated, and
Yep.
So as a woman working in a STEM field, do you have any advice for young women and gender minorities that are looking to break into this type of career?
Yeah, I have a couple more theoretical and more practical pieces of advice, which I think is par for the course for a planetary scientist. I think one of the things that I keep in the back of my mind all the time is that the word scientist was invented to describe a woman who did science. So back in the 19th century, you were a man of science, or you were a botanist or a chemist. And Mary Somerville wrote a book that was a popular kind of science book that was incorporating a lot of different subfields and trying to come up with generally like a physics of how things worked. And in a book review for that book of hers, the reviewer went, well, I can't call her a man of science. And she was also, I think, Lady Mary Somerville. So he's like, okay, I also like have to respect her social position. So I can't like go. It was hard for him to describe who was writing this book. And so that's the first print usage of the word scientist in the English language, is to describe her work. So scientist is a term that was invented for a woman. So I like to keep that in mind, because I call myself a scientist with like very specific intention. Yeah, no one tells you that in your physics undergrad, that a general term for a person who does science in the present day is specifically designed to be gender agnostic. So that's something that, you know, when I'm having a day being like, are people actually listening to me? I'm like, well, you know, there's a long history of women and gender minorities in this field, even if it's not something we think about all the time. The other more practical piece of advice is finding mentors. I definitely was very privileged as an undergraduate to have 2 female research mentors, and it was incredible to be able to see how they had kind of negotiated their careers. At that point, one of them was a postdoctoral scholar with a PhD, and the other one was a tenured faculty member. And it was really interesting to see how they had kind of overcome some of these challenges, and how they suggested that I do work, because none of them ever said, hey, we're both women, we know what the odds are in this field, they're stacked against us in some capacity still even to this day. But it was like here's how you could give a talk, here's how you make sure that you're presenting really high quality research. My undergraduate mentor even said, I was trying to get the room for an astronomy club meeting, but the Society of Physics students was still meeting. And she just pulled me aside and went, you know, you can just kick them out. You booked the room, it's yours. I'm like, okay, if we're going to take that attitude, well, let's go for it. And so seeking out that kind of mentorship, both from people who are the same gender as you, but different genders, and trying to understand that a lot of us in the long term want to kind of raise the next generation of our peers and our collaborators. And so finding someone who's a little bit further along in their career who can give advice and mentorship is something that a lot of us who are kind of post PhD or starting to get on the faculty route really want to see, because we want to improve the conditions for everyone who is working in this field. And we have lessons learned, and your mileage may vary, but the mentorship is always something where I get excited going to these conferences because I get to see my mentors and I get to see people who I have mentored do the next step of their career, and it's incredibly rewarding. So yeah, remember that the word scientist is gender neutral fundamentally, and that this is like 19th century, late 1700s, early 1800s. So this has been, as long as Western science has been a profession, there have been women doing it, and the field has changed its language fundamentally to accommodate them. So like, if you ask for a gender neutral bathroom, that's not saying we need to invent a new word for this new concept of how people do science. So like, ask for the bathroom. And then also finding mentorship, because there are a lot of us who have been in the field and want to help and want to make things not necessarily easier, but to kind of pass on lessons learned from how we've been able to negotiate it. And we want to see people succeed, and we want to see and have colleagues for potentially decades to do really cool, challenging things out there in space. So yeah, that's a long-winded way of saying mentors, and remember that you belong here. And if someone tells you that you don't, that's their problem, it's not yours.
That's great. I love that advice. I think sometimes people come up thinking that they're like an island, and so I like that you were able to illustrate that, this is a community, and people want to work together as a community in the science fields. But yeah, I really appreciate your time today, coming on the show and sharing your insights.
Awesome. Well, thanks so much for the invitation, and it's again great to talk about science in a not purely technical way. And I hope this is useful for folks out there listening who are thinking about careers, or know someone who's thinking about a career in science, that you don't have to take out millions of dollars in student loans. It's nice to hang out with other scientists and talk about science, but also talk about life, and that we're more than happy to have you if this is a career that you're interested in.
Thank you for joining us for this episode of Closing the Gap. If you like this show, subscribe on Spotify. You can also find us on Instagram at MV-STEM-CTE, on Twitter at Mid-Valley STEM, and online at midvalleystem.org. Until next time, keep progressing.